paper, basically, or our talk, is focused mostly on several different values building on the paper from the Rice University researchers. The first one is that we try to find the smallest difference visible from common vantage points. Expanding beyond just Planet Lab, since we don't have access to Planet Lab, we decided to set up our own vantage points. So we configured a bunch of hosts, including LAN to LAN, crossover cables, EC2 to EC2 servers, and then over the internet from a commodity DSL link to EC2 and its dedicated server. We also wanted to profile different languages. So we tried some implementations of standard compare loops in C, Java, Python, Ruby, and some other languages. And we wanted to see how timeable are simple comparison loops in these languages. You know, if you say in Python, you know, A equal B, how long does that take to operate on an average per byte basis? And if you have an exit early type compare, which all languages do, for instance, memcomp and C, standard operators, string compares, things like that, for an optimization, they exit as soon as they find a difference. So that can provide timing information about the secret information if you're working with a secret. So we'll get into that in more detail. And then finally, we wanted to find different types of timing links in multiple implementations of various web auth protocols and, in fact, even OpenSSL. So, and then finally, we want to explain how to exploit them where possible. First question, how small a difference is visible from common vantage points? So this is just a mocked up version, but this is what you want to see. You want to see two distributions that are obviously distinct. So let's say we're comparing a password guess of A versus a password guess of B, and the correct answer is B. And the correct answer, B, is in the yellow here. This is the kind of thing you would like to see. It's easily predictable. As you can see, the two distributions are very distinct. There's very little overlap between them. And even a simple hypothesis test just based on difference of means would detect this kind of difference. What you don't want to see is this. Your two distributions are basically identical with a small number of variations. If you were to try to do hypothesis testing based on this, you'd probably find a lot of false positives, where either you'd find differences where there are none, or false negatives, where you say there are differences there, but you're keying on too small a detail, and it's actually not a good estimator. In this case, what you can do is you can take more samples. When you take more samples, often if the distributions are different, they'll separate. Or it's possible that the difference is just too small to distinguish reliably. And for instance, you know, if you're attacking, you know, picosecond level variations over the internet, not likely to succeed within a realistic amount of time. So people we talked to about these kinds of attacks basically had a few objections up front. One of the first things people said is, you know, well, what about TCP and Nagel algorithm? Is that going to hurt your timing attacks? And we did some analysis of this and found that there's some simple things the client can do to avoid triggering this behavior. So basically, Nagel's algorithm works by avoiding sending small packets when you're doing lots of subsequent writes. So let's say I'm writing the message hello to the server. If I write HELLO in 5 subsequent calls, basically a poor implementation would just send 5 1-byte packets, which is a lot of overhead for TCP/IP. But what Nagel does is it says, let's delay a little bit after each small send. So if you're sending less than the window size, just wait a little while. If another send happens within that timer, then go ahead and combine the 2 sends. So that way you're reducing your overhead. But if you send a large amount of data, then it will send it immediately. So this actually had no effect on our attack because in any particular configuration, because the first packet of the response in Nagel is always sent immediately. So basically, Nagel applies to subsequent messages. So we actually found that no matter what size packet the server was sending as a response, as soon as it generated the first write call, the packet was sent. And we do need to be careful, though, to make sure that there aren't any outstanding acts from the client side, just in case that would trigger some behavior there. So what we can do is, since we can control the client, we basically connect to the server, delay for a few microseconds to make sure everything's settled down a little bit, and then begin sending the requests. Now, on the client side, you can also set an option to disable Nagel, just in case you want to be sure, but you can't affect the server, obviously. The other idea we heard from some people is, well, what about TCP timestamps? So these have been used to fingerprint hosts. You guys familiar with that? Worked a little while back? Yeah. So basically, TCP timestamps are an interesting way of observing the clock on the server side, but unfortunately, they were too low resolution for what we wanted to use them for. Most clocks on servers run about 1,000 hertz, based on the various timers for the scheduling clock, and this is just too low resolution for us. So one thing we thought of, though, possibly based on this was, what if the client could synchronize with the server's timestamp clock by just measuring it repeatedly, and then at some point basically say, okay, we know the server is going to generate a tick in the next 10 microseconds. So then send the request and check the response. If you get the old timestamp, then we got there before the tick happened, and the server responded before the tick happened. If it arrived after that point, then we'd see the next timestamp in the sequence. So this seems like it would be useful, but unfortunately it would only give probably, in our estimation, about a few microseconds of resolution, and we need to try to resolve things down into the nanosecond level. It's also very dependent on the server's timer stability. If the server ticks at a slightly slower or faster rate, maybe based on load, or based on Linux tickless scheduling or other things like that, then this might not be a reliable method. But it's still worth some more looking into, and we haven't done that yet. Some other factors we looked into, IRQ coalescing. So if you have modern gigabit hardware or faster, you usually have this feature enabled in your drivers. And what this does is basically, when your server is under heavy receive load, you don't want to be generating an interrupt for every packet you receive. That'll just overwhelm your server handling all these interrupts, and you won't get any useful work done. So instead of doing that, most drivers set up the Ethernet hardware to actually implement a state machine that says, if I haven't received another packet in a certain amount of time, then go ahead and generate an interrupt. Otherwise, wait a few microseconds or hundreds of microseconds for another packet and then deliver it. And this can add a significant amount of jitter, we found. Basically, we disabled IRQ coalescing on our client, and we also tried with our server and without the server to see how this helped in some scenarios. And this did help for some of the smaller timing variations, but didn't make much difference once you got to some of the larger values. And one thing we'd like to see more work in is more analysis of these different types of networking hardware. I mean, 10 gigabit Ethernet, really fast, low latency, fiber channel. And there's also some analysis of some of the cheaper versus more expensive gigabit adapters. Some of the cheaper ones may do poor coalescing or better. It depends on, that will depend on how exploitable it is. Also, power management. So this is something I have a little bit of experience with. I worked on the FreeBSD ACPI implementation for a long time. And CPU power management is actually quite aggressive these days, especially on servers, where you can vary the frequency and voltage of the clock rate. And then also there's these idle states, where basically you say, if the CPU is not doing anything, go ahead and put it to sleep for a while. And when an interrupt comes in, it'll wake up again and begin processing. And that's used for things like tickless scheduling. Has anyone heard that? A few people? Okay, great. Yeah, tickless scheduling is where instead of setting up your timer to tick 1,000 times a second and you're basically wasting power every time that ticks when there's not work to be done, you basically say, I know I need to handle some work in the next 10 milliseconds. So you set the timer for some point in the future and you change the rate of the timer based on your load. So these things can all affect your measurability of things, both from the server side and from the client side. So on the client side, you definitely want to disable this. What we did was we basically, we set the clock rate to the maximum on our client. We disabled all idle states. And let's see, we did some other things with SMP I'll talk about in a second. On the server side, of course, again, you can't necessarily depend on these things, but you can do some things to take advantage of it. So if you can load up the CPU's, the server CPU's workload, then the server CPU won't go to sleep, and it will tend not to throttle back its clock rate. And so you can get higher precision measurements that way. The TSC is a timestamp on CPUs, 64-bit, and it's basically one tick per clock. And the TSC isn't always the greatest timer, but it does offer really high precision. The value of the TSC may not be synchronized between CPUs on an SMP host, so they may have two different values. And this causes a problem if your client is using the TSC as a timer, because let's say one is at 100,000 and the other one's 150,000, then you'll see widely varying times based on which CPU you get scheduled on. The other thing is, it may not change based on your CPU's clock rate. And so you actually want it to be reliable based on the clock rate. If the clock rate changes and the TSC rate changes in the middle and you're taking a measurement at that time, you can, again, get widely varying results. So what we did was we ran our client single CPU to eliminate scheduling problems. And the server happened to have a reliable TSC that was independent of which clock rate it was running at. And this is becoming more common in modern hardware, so that actually helps an attacker. One idea we had that we haven't seen in previous timing attacks was, what can we do about the kernel and user mode scheduling on the client side? So what we thought of was, well, let's use libpcap and have it do the timestamping of the packets for us, since that happens in the kernel right after the packet's been delivered from the Ethernet driver, but before we've run the user mode process to receive it. And so what we did was we took different measurements. One was just a raw user mode TSC measurement, where we just send a request and then measure the response from user mode around the send and receive calls. And also in kernel mode, we changed the PCAP implementation on our client to use the TSC as the timestamp mechanism instead of the normal microtime. And these are the two distributions we found. As you can see, there's additional latency in the user mode timestamp. However, when you subtract based on the mean difference, you see this. And so we think that this kernel modification, while it was useful to us, did not provide a significant reduction in jitter. And this is the good news for the attacker because it means you don't have to muck around the kernel too much. Just standard user mode timestamping should be sufficient. We also found this was a useful modification because a lot of times we wanted to do some additional processing on the client side to decide if we're going to look at a packet or not, and having to timestamp too close to that was a pain in the butt. So we basically relied on the kernel timestamps because the kernel will queue up the packets after they've been timestamped, and then we can just read them off at our leisure whenever we want to get around to processing them. So let's talk a little bit about noise model. The Rice paper talks a little bit about the channel noise model and estimating it, clock skew and things like that. Basically what the noise model is, every load or pair of servers and clients will have different kinds of noise added to them. Some will have large amounts of noise with high variance. Others might have a long delay but very small variance. For instance, previously the user and kernel mode switching was a long delay but added very little jitter to our measurements. When you look at a model like this, or when you look at the measurements like this, that is usually, the model helps you select a filter. So in this case, for instance, if you look at this particular model, it's a clearly longer distribution with a second mean to it. And if you take those samples there, you basically get what looks like a Gaussian. So when you look at the distribution, that suggests a filter. In this case, I would say, knock off the upper 10 to 15% of these samples, and you'll get a better distribution to do hypothesis testing on. So we analyzed a bunch of different filtering approaches. The first one was the minimum, just basically take the minimum measured value in each set of samples. Take the quickest response time. The second one was peak filter, where basically what you do is you take the peak measurement, the most common measurement of your set, and take the mean of that set of measurements, and that is your characteristic value. The next one was percentile, where you take all the values that are less than X%. So take all the values that are in the fastest 25% of response times. And then finally, percentile range, which was take all the values between X% and Y%. From analyzing all these approaches, we thought that percentile range was actually the best approach. What this would do is it would filter out some of the really fast but high amounts of jitter in the minimum response times, as well as knock off the high end where we saw significant jitter being added. For some of our hosts, actually, the best percentiles were in the range of 2 to 25%, which we called low percentile ranges. But for some other hosts, we found that some of the middle percentiles were actually better. And that's different from what the Rice paper found. They basically focused on the low percentile and low percentile ranges. But we found that for some of the really fast response times, some of the close vantage points like crossover cable and LAN, that sometimes this was the better filter to do.